Welcome back, Earth Science students, to another one of our videos. We are quickly approaching the end of the year and the end of these videos and going into summer. Remember to stay up on your work. You have one assignment this week and also a check. We will be taking the unit test on our chemical reactions unit, I believe 1 week from today. Your final will be due 2 weeks from Sunday, so make sure that you're staying on top of it. We do not have very much time left in our year, but without further ado, let's get into what we're talking about today, which is enthalpy, entropy, and Gibbs free energy. Now, we're in the chemical reactions unit, so we're going to be talking about chemical reactions and the properties that those chemical reactions have. So let's get into it. All right, so enthalpy. These three things, all three of them, enthalpy, entropy, and Gibbs free energy, are what we call state functions. Okay, this means that we only care about the beginning and end values and not really anything that happens in between. They can fluctuate up and down. All I care about is what happens at the beginning and what happens at the end. Enthalpy is a difficult thing to calculate. There's simply a lot of energy contained in bonds and molecules in chemical reactions, and if you wanted to calculate the exact enthalpy, you would have to break every single one of those bonds and calculate the energy individually. Luckily, we have people that have already done that for us, so we can look in tables and look them up and that sort of thing, so you won't be having to do any of those crazy calculations like that says, but just know that that is where we are getting to. Okay, so just to give you an idea of finding enthalpy, okay, I do this analogy. Find total enthalpy is like finding the total amount of water in all of the oceans. Good luck trying to find the exact amount. Okay, so if I wanted to know exactly how many liters were in the ocean, it would take a long time to figure out. It would be almost impossible to figure out because it's constantly changing. However, if I dumped a 2-liter bottle of water into the ocean, I do know that I just increased that amount in the ocean by 2 liters. For this reason, we care much more about the change in enthalpy than the actual enthalpy itself. So you'll see me say a lot of delta H is how it's represented. Enthalpy is delta H, and that just means the change in enthalpy. Okay, we don't care about what the actual total enthalpy is. We talk about how it's changing, because like I said, it's very difficult to calculate the entire thing. So instead, we just focus on the changes in enthalpy. Okay, so now that I have talked about enthalpy, let's talk about what it actually is in a chemical reaction. So in a chemical reaction, these different elements are reacting with each other, and what happens is that heat and thermal energy are either gained or lost by the system. And so remember, we also have the law of conservation of energy, meaning that we don't actually create or destroy energy. All it is either lost to the environment or gained to the system. We all have the same energy all the time, whether or not we lose it or gain it from the environment. You guys will remember when we did the energy unit and we talked about car crashes and that sort of thing, that we don't lose any of that energy, it just gets transformed into different forms. Okay, so how is enthalpy measured? This is measured by using temperature changes. So if enthalpy is all about heat and thermal energy, then it's very easy to just take the temperature and see how the temperature changes, and we use that to calculate our change in enthalpy. These temperature changes are caused by the changing and breaking of chemical bonds in a reaction. Okay, so if you think about a chemical reaction like burning something, okay, the chemicals are changing because of the reaction, and the temperature obviously changes as well. So we can measure that temperature and we can decide how much enthalpy, or decide what the change in enthalpy would be based on that temperature change. Okay, so for example, I think a lot of you have probably used these hand warmers before. Okay, they come in those little packs. Basically, you shake them up and they start warming up. Maybe you guys have wondered, why does this happen? But it all has to come down to, it all comes down to chemistry and enthalpy reactions. So basically what's inside there is solid iron, okay? And what happens is then when you take it out of the package and you shake it, you're introducing oxygen, and it creates, or it reacts together. The iron reacts with the oxygen or the O2 to create something new. And so you can see my chemical equation, that is iron plus oxygen equals iron oxide. And so this reaction, okay, gives off a lot of heat energy, which is what will warm your hands. So what can then be said about the relationship between endo versus exothermic reactions and enthalpy? Well, exothermic reactions are things that give off heat, and endothermic reactions are things that take in heat. Okay, usually before we do these notes, we do a couple of cool experiments. Obviously, we don't have the chemicals, and I don't want to send any home with you or have you try anything without supervision. So usually we would do these experiments where we put two chemicals in a bag, and you can literally feel on the outside of the bag that it is getting freezing cold. It's actually how they make ice packs. And then there's another one that it's starting to get really warm. Okay, so what you need to know, make sure that you write this down with exothermic and endothermic. When the change in enthalpy, or delta H, is negative, thermal energy is being released to the surroundings or lost to the surrounding, making it exothermic. Okay, so make sure that you relate that to exiting. Okay, so the thermal energy is leaving or exiting the system and going to the surroundings. So it's going to warm up the things around it. So when you go back to the hand warmers, the hand warmer itself is the system, and it's giving off heat to the hands or whatever is around it. Okay? When the change in enthalpy is positive, thermal energy is absorbed by the surroundings, meaning the reaction is endothermic. Well, if it's absorbing all the heat, then everything around it is going to get cold. Okay, so this is how an ice pack works. If you ever wondered why, if you have an ice pack, they always tell you there's a little like bag in there that you have to break. Okay, so if you've ever done that, you push on it, okay, it causes a chemical reaction, and it causes the whole thing to start to freeze because it gets so cold. Again, that's a chemical reaction, and it's just literally how these elements and these molecules react with each other, and how the thermal energy is either absorbed or lost to the surroundings. Okay, so that's enthalpy. Enthalpy has everything to do with heat. Okay, so enthalpy, heat. Delta H, a lot of people just call it change in heat because it's an H. That's not technically what it's about, but if that helps you remember, go with that. Okay, entropy. So the first thing we have to talk about is the second law of thermodynamics, states that any spontaneous process increases the disorder of the universe. Okay, so again, spontaneous meaning able to happen without an outside force or outside source of energy. Okay, but we have all these other words, and what does that even mean? Okay, so let's see a different way to think about it. Okay, so think about the food that you eat. The molecules and the energy basically that are held in the bonds of that food that are broken down in your digestive system are ordered before you consume them. Okay, so when you eat let's say you eat a piece of pizza, okay, that is ordered in a specific way, okay, specifically probably to taste good, hopefully, okay, and then you consume them, okay, so they are arranged in a specific way. When consumed, the spontaneous reactions in your stomach begin to break these molecules down in order to give you energy. Okay, so let's say, for example, an athlete eats a protein bar before working out to have energy to actually do the workout. Does 100% of the energy from the bar go directly to the muscles required to work out? Hopefully you answered, well, no, not 100%, okay, because some of my energy goes to processes that in our body that we don't control, like breathing, blinking. There's other processes that are going on behind the scenes that we don't see. Okay, making sure that our liver is working, making sure our kidneys are working, all that stuff. Literally just me sitting here requires some energy. Okay, and so we get that from the food that we eat. Okay, so the answer is no. The energy from the bar becomes much more random. It goes to random things. It is not centralized to be like, I want all this energy to go here. Some goes to the heart to keep it beating. Some is used to create sweat to regulate body temperature. Some is actually used to move the muscles to do the workout like you wanted, and many other things. The protein bar began as a specific order of molecules, and now that energy has become scattered to multiple things. So when we're talking second law of thermodynamics, we're talking about going from order to less ordered. Okay, a lot of people like to think of it as like going from a solid to a gas. Okay, solids are very ordered, and then as they melt, they become liquids, and then as they either evaporate or boil, okay, then they go to a gas and they're less ordered. Okay, they're more chaotic. Okay, so a lot of people say disorder or randomness or chaos when they talk about entropy. So everything we're talking about is just increasing the disorder of the molecules in the universe. Okay, so like I said before, entropy is also a state function just like enthalpy, so we don't really care about the total entropy of a system. We care about how it changes. Okay, so after the reaction is occurring, what is the disorder? Is it going up? Is it going down? Is it making the reaction increase the disorder of the universe or decrease it? Okay, so entropy is the measure of molecular randomness or disorder. Okay, so how do we see entropy? Because it's a very difficult topic to think about, especially online when I don't get to actually talk to you guys one-on-one. So how does entropy relate to our frozen wood block demonstration? So I posted another video that I usually do the same one in class, where you mix two chemicals together. They create an endothermic reaction that will let my beaker stick to a block of wood. Okay, so solids, so they start out as two solids. They're much more ordered, come together and form liquids, and gases more disordered. Okay, so that's going to increase entropy. Okay, so whenever you go from ordered to disordered, that's increasing entropy. So our delta S is for entropy. Delta S is going to be positive. Okay. More importantly, energy from the reaction was used to change or break bonds and intermolecular attractions to increase entropy to keep the reaction going. Okay, so the entropy of our block of wood demonstration can be calculated to be 0.594 kilojoules per Kelvin. Okay, so like I said, when positive changes in enthalpy means that actually those should both say entropy. I'm going to need to change that for future reference, but those should say entropy. So positive changes in entropy means that the disorder has increased. Negative changes in entropy mean that the disorder has decreased. Okay, so make sure, don't write enthalpy, write entropy. I'll change it for future reference, but don't want to stop the video right this second. Okay, so positive changes, so positive delta S or positive changes in entropy, disorder increases. Negative changes in entropy or negative delta S's mean that the disorder has decreased. All right, and so the last topic that we need to talk about is Gibbs free energy. And this is really just the way that we end up using the energy that is created through chemical reaction. So the energy associated with the chemical reaction that can be used to do work. Okay, so work is basically having the energy to do something. Anything that you need, whether it's pushing something or pulling something, or if you even think about like our energy, how we use electrical energy to do work, that sort of thing. Hey, in other words, we use chemical reactions to make something happen, and when we do that, we use the energy that is produced in the reaction, known as Gibbs free energy. Okay, so Gibbs free energy talks about being spontaneous or non-spontaneous. Okay, those two things. So just like enthalpy, changes in enthalpy was exothermic or endothermic. Okay, and then changes in entropy either increase disorder or decrease disorder. Gibbs free energy tells you whether a chemical reaction is spontaneous or non-spontaneous. So we have this equation that calculates Gibbs free energy for us. Hey, delta G is Gibbs free energy, delta H is our enthalpy, delta S is our change in entropy, and T is our temperature in Kelvin. Okay, and one thing to make sure that you remember is that at absolute zero, which is when Kelvin is zero, that is when all of the molecules basically can't move anymore. So all of this chemistry stuff that we talk about ceases to work at that temperature because it's so low that we can't even have like any interactions between molecules. So what you need to write down, when delta G, when Gibbs free energy is greater than zero or positive, okay, we say that the chemical reaction is non-spontaneous. Another word you might see in chemistry textbooks is called endergonic. Okay, so we're going to use spontaneous and non-spontaneous just to keep it clear, but ender versus exergonic is also something that people use. When delta G is negative or less than zero, we say the chemical reaction is spontaneous or exergonic. Now, I know what you're thinking. Okay, well, what do I mean by being spontaneous versus non-spontaneous? Okay, so a spontaneous reaction is capable of proceeding in a given direction without needing any outside source of energy, meaning that if it's a spontaneous reaction, I have these elements and I have the correct situation, the correct environment, and that sort of thing, that reaction will happen without me doing anything to it. Okay? A non-spontaneous reaction is not capable of doing that. That means that it is either in an environment or requires some extra help in order to occur. Okay? Otherwise, those two molecules or elements are just going to sit there and they're not going to react until they get that help. Okay, so what they usually do is they pair a non-spontaneous reaction with a spontaneous one, and the energy from the spontaneous one will give enough energy to the non-spontaneous one to happen in sort of like a chain reaction situation. Okay, so how do we know when a reaction is spontaneous or non-spontaneous? Really, all we do is we look at the equation. Okay, so we use enthalpy, temperature, and entropy to calculate these things. So delta H can either be positive or negative. T can only really be positive because at 0 Kelvin, atoms and molecules don't move, so you know that T is always going to be positive, and it's getting multiplied by delta S, which can be positive or negative. And so what we do is we kind of look at these as, okay, well, if delta H is negative and delta S is negative, I'm going to have a negative, but then I have a minus sign, a negative. Okay, and so you'll have to think again back to math. When I subtract a negative, that is going to change to a positive, and so I'll have a negative plus something, and that is kind of how we figure out and go through how something is spontaneous or non-spontaneous. I have it summarized here on this last slide that I have. Okay, so a lot of information. I'm going to try to go through it step by step and try to explain how we come up with everything. Okay, so let's start out with delta H being positive. So that means enthalpy is positive. Okay, delta S, positive. Okay, so if you look at your equation, and both of these are positive numbers, okay, notice that if I have a positive minus another positive, that it kind of depends on whether or not that's going to be the result is going to be a positive or negative. I could have 100 minus 50, and that would be a positive number. But I could have 50 minus 100, and that would be a negative number. So you'll notice that for the delta G, or Gibbs free energy, I say it depends on what the temperature is. If the temperature is really, really low, okay, then this is going to tend to be negative. So let's say the temperature was 10. Okay, well, then this is going to be something big minus something small, which is going to be a positive number. And then vice versa, positive at high temps. So let's say it's at 1000. Okay, well, something small minus something big is going to give you a negative. Okay, and then in the last column, it's very, very important that you guys can keep these vocab words together. Okay, so the description of the reaction, it's endothermic because it has a positive enthalpy. It increases disorder because it has a positive entropy. And technically, it can be either spontaneous or non-spontaneous depending on the temperature. All right, so if we look at the next one, positive enthalpy, negative entropy. Okay, let me erase here real quick. We'll talk about how we know that delta G is going to be positive. Okay, so if delta H is positive, okay, so we're starting out with a positive number, and I know that delta S is negative, okay, I'm going to get a situation here where I'm taking a positive minus a negative. And remember that when you minus a negative or subtract a negative, that is the same thing as adding. Okay, so double negatives create positives. So I know that a positive plus another positive is going to end up positive. So that makes for an easy transition where I can say that the reaction is endothermic because enthalpy is positive. It decreases disorder because entropy is negative, and it's non-spontaneous because delta G, or Gibbs free energy, is positive. Okay, so if you think about what that means in terms, endothermic means that it is absorbing energy, it's decreasing the disorder, so it's like pulling things in. Okay, you can think of it kind of like freezing. Okay, so it's freezing things, and it's non-spontaneous. It's not going to happen unless it has a source of outside energy to occur. All right, and then the next one, we change delta H to a negative. Okay, let me erase here. Okay, so delta H is now negative. Okay, and we're going to make delta S a negative as well. Okay, and this is going to be another situation where it kind of depends. Okay, if delta H is negative, and then this is going to be a plus sign because I'm going to have a double negative here with delta S and T. Okay, so it kind of depends how much I add. If delta H is really big and T is really small, then I'm not going to add enough to get back to positive. It's still going to be negative. But if I have a really high temperature, then I'm going to be positive because I'm going to add a really, really big number. Okay, and so then again with the description, now that our delta H is negative, we can say it's exothermic, so it's giving off heat. It's decreasing the disorder because of the negative delta S. It can be either spontaneous or non-spontaneous depending on the temperature. All right, last one. Okay, negative H, or delta H, positive delta S. Okay, so let me put in a plus sign right here. Okay, so that means that T times delta S is going to be a positive number. Well, if I take a negative delta H minus a positive number, I'm going to get more negative. Okay, so no matter what, delta G is going to be a negative. Okay, if you guys need to sub in numbers to see that, just go for it. So like if delta H is, let's say, negative 10, okay, minus, I'm just going to do 1 Kelvin times just any positive number, we'll say 7. Okay, well 1 times 7, remember you have to do multiplication before you subtract. 1 times 7 is 7. Negative 10 minus 7 is still going to be negative. It's going to be negative 17. No matter what positive number I change delta S to, I'm still going to be subtracting. I'm still going to be getting more negative. Okay, which is why I can say that delta G has to be negative. And then lastly, for the description, I can say exothermic gives off heat because delta H is negative. I can say increases disorder because it's positive, delta S, or positive entropy. And then it is spontaneous, meaning it doesn't need its own outside energy in order to occur. Okay, that is all I have for you for these 3 things. Hopefully they make sense. If they don't, make sure that you're popping into office hours or sending me an email and we can meet privately. Either way, don't go this entire place just being, or this entire quarter being confused. Reach out to me. I'm here to help. Just let me know. And as always, thanks for watching.